Welcome back. Now we are going to discuss about some results which relates uniform convergence and continuity concept. As you can see, we are going to start our discussion with the theorem which says that if Fn converges to F uniformly on some set in a metric space X and X be a limit point of that set E, and suppose that limit t approaches x fn of t, that we are taking it as an, then this an form a sequence which converges, and this limit of this sequence would be same as that of the limit of convergence. Okay, so in other words, what we can write is that limit t approaches x, what is this f of t? It is limit n approaches infinity fn of t, isn't it? And here limit n approaches infinity, what is this an? It is nothing but limit t approaches x fn of t. So the interchange of these limits is possible. That is what we are gonna prove in this theorem, and at the end we will see the inference that we can make from this theorem. Okay, first of all, what is given? Fn converges to F uniformly on a set E. So by definition of uniform convergence, for given epsilon positive, there exists n such that small n bigger than or equals big N and small m bigger than or equals big M, and for all t in the set E, we have absolute of fn of t minus fm of t is smaller than or equals epsilon. This is by the definition of uniform convergence. Okay, and what is given? Limit t approaches x fn of t an is given. Okay, now if we take limit here, that is limit t approaches x absolute of fn of t minus fm of t less than or equals epsilon. Okay, and this epsilon is independent of t, and that is why the limit doesn't affect on the right hand side. So this shall be written as, since this absolute is a continuous function on any set, this limit can be taken inside. So this will be limit t approaches x fn of t minus limit t approaches x fm of t, using the properties of continuous functions. So this will give us what? Absolute of an minus am is less than or equals epsilon, right? And this is true for n bigger than or equals n and m bigger than or equals n. This proves our sequence an is Cauchy. As you all remember, we are dealing with the sequences on real or complex. So it is Cauchy in a Euclidean space, which is complete. Therefore, this an converges, okay, to some limit that we call it as a. Okay, now what should we prove? We should establish this limit t approaches x f of t is same as that of limit n approaches infinity an, and here what we have said, an converges to a, that means limit n approaches infinity an is a. So we will have to prove what? Limit t approaches x f of t is same as that of a. Limit t approaches x f of t is a. This is what we need to prove. For that purpose, what should we do? We will have to prove absolute of f of t minus a is less than epsilon or less than or equals epsilon whenever absolute of t minus x is less than delta. So this is what we should do now. Okay. For that purpose, let me consider absolute of f of t minus a. Now what am I going to do is that I am adding and subtracting fn of t, then an. So using triangle inequality, this is f of t minus fn of t plus fn of t minus an plus an minus a. Okay, this let me mark it as equation 1. We choose n such that absolute of f of t minus fn of t is less than or equals epsilon upon 3. This is due to the fact that fn of t converges to f uniformly. So we would be able to identify one such big n such that this is happening. Okay, and here this is true for all t in E, right? Okay, and this n is chosen in a way that this is happening. Okay, also absolute of an minus a is also less than or equals epsilon upon 3. This is due to the fact that this an converges to a. Okay, so we are choosing one such big n such that these two are happening. Now what are we gonna do is that then for this particular chosen n, we choose a neighborhood that neighborhood we call it as v of the point x such that absolute of fn of t minus an is less than or equals epsilon upon 3 if this t is a member of v intersection E and this t is not same as x. So that is basically we are trying to check the limit at x. Okay, limit as t approaches to x. So around x we are choosing a neighborhood. That neighborhood based on this n we are identifying. So the radius of the neighborhood may involve this n. Okay, accordingly we will have to identify one such neighborhood such that this is happening. Now, so substituting the above all into in equation 1, what are we getting? Absolute of f of t minus a is less than or equals epsilon upon 3 plus epsilon upon 3 plus epsilon upon 3, which is absolute of f of t minus a is less than or equals epsilon, provided t is a member of v intersection E. Okay, so when I was explaining, I told you that whenever absolute of t minus x is less than delta, this is what I told you. But is it a valid argument here? It is valid when your metric space is a set of real numbers. So basically what should be the case? We should get t in some neighborhood, some delta neighborhood of x. Okay, that neighborhood we have named v here. So we just proved what is required. Okay, with which what can we conclude? This proved that limit t approaches x, f of t is nothing but a. This a is what? This is limit n approaches infinity an. Okay, and what is this f of t? That is limit n approaches infinity fn of t. And what is this an? It is limit t approaches x fn of t. So we just proved this theorem. Moving further, next we have a theorem which says if fn is a sequence of continuous functions on E, and if fn converges to f uniformly on E, then f is continuous on E. So we are not going to actually prove this theorem, but I can brief you the outline of this proof. Given that fn is a sequence of continuous functions on E, that means for any x in E, your limit t approaches x, fn of t is nothing but fn of x. Okay, and fn converges to f uniformly on E. That means your limit n approaches infinity fn of t is f of t for all t in E, and absolute of fn of t minus f of t is less than epsilon for n bigger than or equals n. This is what this says. Okay, and what should we prove? We will have to prove f is continuous. So one of the equivalent statement of continuity is limit t approaches x, f of t is same as that of f of x. Is it enough to prove this statement? Okay. Now consider limit t approaches x, f of t. But what is f of t? It is limit n approaches infinity fn of t. We just have proved that if the convergence is uniform, then the limit can be interchanged, right? So this shall be written as limit n approaches infinity, limit t approaches x, fn of t. And what is this limit t approaches x, fn of t? It is fn of x. And this is true for all. Here it was true for all t in E. So the convergence is uniform, therefore it should be f of x. So we just proved limit t approaches x, f of t is same as that of f of x. Therefore f is continuous on E. Whenever we have a sequence of functions which is continuous on E and uniform convergence is there, then the limit of the sequence is also continuous on the given set E. That's it. Thank you.